Hello, how are you doing? Welcome back to CIS11. We'll start in about a minute. So let's take a look at your Canvas assignment and your Unit 6 notes. Okay, so let me share screen. Okay, so this week we are going to work on additional solving problem and debugging in LC3. You will be able to find your notes in Canvas here and also your assignment. So right now we are going to take a look at our notes and we're going to go over the concept and we're going to answer some of the questions, which will require you to do snippet of LC3 programming. So we're going to go ahead and do that. Okay. Any question before we start? Okay, so hopefully more people will be able to join us. Also, I will be updating your grades today and tomorrow later on tonight, as I had to work on a few things for various stuff for the admin side today. So I will get your grade done in the next today and tomorrow. Okay. So in chapter 6, it's going to go into some of the details about how we would approach solving a problem, as you saw how we would use LC3 to be able to output days of the week, month of the year. We started doing this already, but we need to really break down the requirement into pieces so we can interpret that into an algorithm or what we would see procedure to solve a problem. So in problem solving, we would use a structured programming concept. It is a way for us to take a complex problem and decompose it into smaller, manageable pieces. And this is going to help you think about how you would incorporate your subroutine or your functions in your program. And so here it talks about how we would create, or we would take the problem description, which is going to give us the criteria of the problem, and we would break it down into the smaller manageable units. And for students, I feel that if you go through the Pseudo Code process, you would also be able to look at how to derive a solution for your problem, and also to look at how your program flow would be. And here we're going to talk about the systematic decomposition. One second, let me turn on live transcript real quick. Which allows us to take a larger task and break it up into the smaller tasks. And this is going to help us think about how we would use label and subroutine, which is equivalent to what you see in function in C or C++. Okay, so here it defines what a systematic composition is. So we would take the bigger problem, break it into the subtask, which then we can also break it into the smaller subtask, and so on. And at the machine level, we want to be able to see that. We want to be able to go to the simplest task where we would incorporate that into what you see with instructions. And so what do we need to really think about how we would break that into the smaller task? We need to convert the problem statement into an algorithm. And an algorithm is just a procedure that we would apply to the program. So it would incorporate the step-by-step process on how it would go from one subtask to the next subtask. So here it talks about how we would define the stepwise, or we would refine it. And once you break it down into procedure, you can take a look at the individual step and improve the individual step. So if you have the algorithm created from the problem statement, then you can use that algorithm for your machine solution, which we would apply in LC3, where we would implement the instructions, the opcode, and the operand. So here it gives you an overview diagram. So you would take a task, and then you would start with creating the subtask. And then from there, right, you would apply certain conditions, if that's part of the problem, to the subtask. And then we will be able to test the conditions. So in a program, you would see that we can use the sequential approach, where it will be top down, or in most cases, we would have to apply conditions, where that will be, using if-else statement, or in our case, we would use a label and branch. And then, or we would implement a loop. So in the last lab, we had used iterative approach, where we would have a continuous non-ending while loop. So here you would be able to include that area, and we can use a label to do that. We can branch, we can check based on the condition for whether it's true or false. If it's in a certain condition, we can have it exit the program. So in the sequential approach, this is what you normally see, that we would execute the first task, and then it will move into the next task. And so it will just be a top-down flow. And you see this in higher level programming, right? In the case of C++, we define a function, and then we call that function in main, and then we call the next function after we return from the first. So in Python, you really see it, and it's really transparent through the interpreter, where it's just going to execute each line, right? It's going to interpret each line, and it's going to complete the task that you tell it. So now in the sequential approach, most of the time you do see that it is slow, right? And in the case that if it doesn't complete a certain task in the middle, it will not get to the end of the program. So you do run into some issues with sequential, but a lot of the times you would see this is the traditional approach, where it will be top down. Then for the condition, we talked about conditional, where we would check to see if a certain condition is true, like if-else statement. And so if it is true, then it's going to do the subtask 1. Otherwise, else, it's going to go and do the subtask 2. So you can break it up into the 2 subtasks using conditional approach. Okay. And then third, we talked about iterative, in the case where we would see this implemented in a loop, right? It's going to loop as long as the condition is true. So that will be like your do while or your while loop. Or in some case, we would also implement iterative when we're using a for loop. So as it checks a condition, it will go and it's going to continue the count. And then when it gets to 0, we're going to have it branch, and it's going to exit that loop. So it depends on what is the problem statement. You can think about how you would be including, right, your approach, or custom your approach based on that. And for your course project or your final project, you would need to implement conditional, iterative, and some part will be sequential. So to answer the question, we can go to our assignment. For number 1, how can you use problem-solving techniques in assembly programming? Describe the process of solving a problem using programming. And we would first derive a problem statement sometime from the questions. Okay, so let me correct this. And in the case where if you're solving this problem for a client or in a business environment, you would need to ask the client the questions, right? And to find out the specifics so you can identify the components that you would need to be able to solve that problem. So we want to really derive a problem statement first, and that's going to help us create or build our algorithm. So after that, the next step, we're going to convert the problem statement into a step-by-step description of subtasks. And that's going to help you plan for your approach in your program. So in the case of our course project, right, you are given various cases. And once you pick the case, you're going to define or derive your problem statement. And from there, you will be able to create your algorithm and write in assembly, which is the third step. So we would correlate 3 of the basic construct, which is sequential, conditional, and iterative, to machine instruction. And that will be your opcode and your operand. Now, some of the requirement would be related to cryptography, where we would write a program that's going to encrypt and decrypt, or we would do a sort program, right, for the project, like a bubble sort, where you would write it in assembly. And if you understand how to do that in the higher language, you should be able to take that and put it into the assembly level. So simply looking at the problem statement, you're going to be able to break down the steps and achieve your goal, which is to solve the problem. So when we use LC3 instruction encode, we would think about our sequential. We talked about that, where it would flow from one to the next. So no special instruction is needed in the case where it would go from one subtask to the next subtask and so on until it finished. Now, in the conditional and iterative, we would need to convert the condition using our branches for negative, 0, and positive. And so you would always use the branch. Now, some case we might need to branch unconditionally, right? You saw that we can do a branch, which is a jump. It will go to a label and it will execute what's in that label. So when it picks up from that label, it's actually sequential. And then the last step is to really make a decision on what to include or exclude in your program and document it. So the things that I'm going to look for on the project is to make sure that you understand, apply the concept, of course, but to really think about how you're solving the problem in an effective way, right? Your decision-making process here, you need to think about alternative solutions that would be solving the same problem. And so you would need to decide on which approach would be most effective for your program, right? As we understand that our program will improve over time, we want to think about, okay, so this is one approach, but there is an alternative approach on how we can make the program could be simpler or could be faster or more efficient. So we want to strive for performance and efficiency. Any question regarding this? You can pull this from the notes, of course. So after number 1, and before we get to number 2, right, you can go to the problem statement. Okay, so here it walks you through the step. Okay, derive the problem statement. For example, where is the file located? How big is it? What would be the final count and the output? What would it be looking like? Okay, if the characters is a letter, do I count both uppercase and lowercase in the occurrences? So that's just an example. You should convert your problem statement into a step-by-step description. So you should start asking the questions. What is the starting state of your problem? What is your final outcome should be? What is the ending state? Right, as we understand that it would be a state machine where it would change as you include the instructions and modify the data. How do we move from one state to another? Are you using functions to be able to do that? Are you looping through that? What will be your approach? Okay. And then the three construct, we can think about if, for, do, while, right? Whether you wanted to use conditional or iterative. Okay. And here again, this is where I pull the answer for your number 1. Okay. Now, for the conditions, it's important that we document the branches, and I emphasize that in all my programming classes. So even if you write it in Python or C++ or Java, you really want to specify what kind of subtask, right, is executing in the case that it's true or false. And it's really important because that's how the program can move or flow in one direction or the other. Okay. And then after that, we would want to get to the next subtask where it's going to sequentially flow down again. So in LC3, what it will do is when we generate that, right, this condition is going to impact what's in your program counter. Okay. And how it's going to use your arithmetic logic unit for the operations as it's going to check the conditions. And so we simply, when we branch, it's going to be negative, positive, or 0. So when those flags are set and activated, your processor is going to use, right? It's going to queue specific tasks based on a certain condition. Okay. And so therefore, it's going to utilize a certain address that's going to be in the memory in order to execute certain things. So it's important to really visualize that and understand that, so that way you can understand, right, how your resources are used, how instructions are implemented, and what the processor really sees. Okay. Now here it talks about the PC offsets at a certain address. So in the subtask 1, it's going to rely on the offset C, compared to the subtask 2, it's going to rely on the offset D. So as you can see, that will be at 2 separate locations at the low level. Okay. And so the bits really represent how you would be branching. Is it an unconditional branch where all the bits are on? And so if you set it where it would branch based on positive, negative, or 0, then these bits would then take effect, and that's how it's going to carry through to understand that this is going to be the subtask that it's going to execute. And so here, right, again, you would see how that would flow in the case where if we have the iteration. So as we only have one subtask here, so when this tests true, right, in the way that we loop, it's going to execute this. So it's going to use the PC offset is going to go to the address C. And depending on the condition of the bits here, right, it's going to execute this subtask. And then when it finished, right, it's going to go to this address, which is offset A. And then it's going to go into the next subtask. So as you look at how iterative compared to conditional, right, the way that it uses resources is slightly different. Okay. And again, in this class, right, we would think about how our processor using our storage. And that's what mostly is on the low level for software. So for this example, this is a program that counts characters, okay? So when you map this out, when you do your flow chart, you think about the start, right? And how it's going to halt at a certain spot, or it's going to flow through and finish till the end of the program. So we understand that the user must input a character, right? And so in LC3, we can think about, oh, I can use a getC, okay, to start, and that's going to be at register 0. And then as they input the additional character, we have to move and ASCII convert it, okay? So that will go into the algorithm here. So we can, input the character, set the pointer for the location, then we can get the first character to the file, or in our case, we would ASCII convert it, move it to another register, right? So the register would hold that, and then we would continue to do that for all the subsequent character, okay? Now, if you need to put that on the file, then we need to make sure that the file has a location in the memory, right? Like if you're using like CStream for a file, like you stream to all the characters to the file. So when the user type in something, it's going to output a text file. So in that case, the compiler, what it does, it sets up a location where that text file is going to be located. And so for every input character, it's gonna convert it. In our case, we see that as an ASCII conversion, take it as a numerical value. When it stores that to memory, it's still a numerical value, but then when it output it onto a file, it needs to convert it back into text and link that, right? Set that address to what you would see in the file when it's streamed. So in the low level, you can see that just this entire process, right, require multiple substeps, okay? All the subtasks that's going to be involved just to get your character ready and how that will be put into a certain location. Now here they show on how we can implement where we would be able to refine a certain step, okay? So in this case, we can scan the file and then we can increment the character or the counter for the character to match. And so we would then have to nest a condition in that. So if that's true, right, then it's going to do the testing. If it's not matching, then it's going to get the next character. So you can nest another branch within. Okay. And we would continue to do that until we get the product that we want. So it is, sometimes flowchart takes a little bit to do, but the first iteration of your flowchart, you have to step back and say, is that effective, right? Can I do something better? Can I make, right? Can I improve my algorithm? Can I make the branches better? Can I test a certain condition within instead of waiting, until the later steps? So as we go through and build our program, we would need to fix some of the areas, and that would get into the debugging, right? So some of the things that, so whenever that you ask me, oh, I'm having issue with this, it's not outputting what I want, or when I don't know why it's not branching, right? Or I don't understand why it's not going to that label. So you really have to use, right, your logic to really think about, okay, so if it's not going to a certain area, you should be able to check the condition before that label, right? Before the branches. So looking at your registers and what's being held with that register and your memory location is very important, okay? You can definitely set breakpoints on your simulator to be able to test, right, to a certain part of your program, or you can step over or step through your program. Now, when you go through and write your problem statement or dissect your problem statement to break it down further, if you take the time to really go into the detail with it, right, examine it and making sure that you set up your subtasks, it will help reduce the debugging process down the line, right? Instead of just writing something and edit it as you go along, that can make the process much longer. I've seen students done that in my programming classes, where they don't really have a plan. They just start programming, and then they realize that halfway through they need to add something. So they go back and they redefine another container or a variable, and then that changes, right, all the other elements in the program. So if you have a thorough plan at the beginning and looking at what kind of registers you're using, how you're using the memory, what kind of processes and sub-processes that you're implementing, that's going to help you, you know, with the process, and also fixing the program is going to be easier. So we need to look at the sequence of instructions to be executed top down from start to end. Okay, that's the overall picture. Then when we go through that, we want to also keep track of the results, right? Why am I commenting every line for you so far? So that way you can see at this step, this register holds this. Okay, so we want to track and make sure that the results is going to give us accuracy output. Accurate output is important. Then we want to compare the result to other instructions to the expected results. So is it going to be matching, right? If you're using, if you're getting the result from each of the instruction. So when I load at the beginning and I go through and I add, right, and I operate, and sometimes I clear register and I continue to add again, am I going to get the same result, right, at the end when I store out? So when you put that onto memory, your expected result should be accurate. Okay. All right. Now, for assembly, right, your values in memory and registers are essential. Doesn't matter what programming language for assembly that you use. Okay. And to store the values into the memory and register, that should correlate. And as you can see, sometimes you would see some value in the registers, and sometimes we would have to store out to the memory to be able to track it, right? Because assembly is not really designed to give you a lot of the interface, right? You need to really see, right, at this point in the memory, it should have this value. And when we execute instruction in a certain sequence of the program, right, on how it's going to flow through, we want to make sure that our instructions are going to be effective. And when we need to stop execution, we can halt, and that will just trap out. Okay. So for the next question, we can say that when you go through the debugging process, very important, right, that we need to check syntax error. Now, sometimes the program builds and it has no error, right? For example, I type add R1 hex 1 or add R1 hex 0, right? But I intended to do an R1 hex 0. It's going to build, but two separate instructions. I'm supposed to do an and instead of an add, but I typed it as an add. So sometimes we need to check it, right? If we're not getting the appropriate result. So check your syntax, check for logic error. Okay, so if it's not branching like how it should, it's not going to a certain label, or you're not getting the result in the memory as it's expected, check your logic. And then also check for data. What value should be in a certain location, or what value is used at a certain register. Any question with this? And for 3, we would define systematic decomposition. That is a way for us to decompose each task into smaller subtasks and even smaller subtasks after that, so we can get to the instruction level for the machine. And as you can see that the task that we normally deal with in the higher programming language, right, it has to be even at breaking down into many more subtasks for assembly. Just to simply do a prompt for us, right, require multiple steps in assembly instead of just doing a cout to a variable, right? And then for number 4, how should a program be debugged? Describe the step for the debugging, and that was included in the note. We would examine the sequence of instructions being executed. So you would look through the instructions. We would keep track of the results being produced. And we would compare result from each instruction to the expected results. And as you practice, right, building out your lab exercises, you would see, okay, as I walk you through this, and when you do your project, you're not going to have a templated example for you to use. You can go back to your lab and you can think about, okay, so how were these instructions written? What can I implement to be able to solve the problem specific for the project criteria? So for number 5, the type of errors that we normally see, right? So if you type in load, like LOAD instead of LD, that's just simply a syntax error. And when you assemble your program, it will tell you, right, a certain line has syntax error. If the output of your program yields negative value, right, for x plus y in the absolute, right, is greater than 0, that should be a logical error. For 5B. And for 5C, if your data input value is less than the given expected test value in the problem statement, that's your data error. And we also have to pay attention to how we're using hex compared to decimal, right? Because decimal has a ceiling where we would be able to use from 0 through 9. And then if you're using anything above 9, you have to treat it as a hex value like A, B, C, D, E, and so on. Any question? So this is easy. You can find all of this in the notes. Okay. And I tried to use the assignment to really help you review for some of the things that you've learned in LC3, because I understand that it takes time. You know, some of you pick this up very quickly, or while others just going to take a little practice to really get it. And I hope that when we do the assignments together, as we go through it, you know, it's gonna help you remember, or it's gonna click. Okay. Okay. So for 6, let's start with this. So what I did was, we can take a program like, you know, what we would see in the lab. Normally they would start with telling you like the location of certain variable, and we can break it into pieces so that way it's digestible. And then when we put it together, it's not overwhelming, right? Because sometimes it's a 1-sentence problem statement. So you would have to, you know, cut it into smaller pieces so that way you can translate it into the machine instruction. So here we want to kind of fill it out with LC3 code. Okay, so for 6, it tells you to create an assembly program that contains the following criteria. X is set to the location hex 3400. That's easy, right? So we can say, oh, we'll just go ahead and fill it. So we would declare the label of X. And so we would put that at the end of our program in the data section. Okay, we would do a hex fill or x.fill hex 3400. So at this time, when you see this, right, or even when you look at a problem and it has variable, you should think about filling. Okay, put it to a memory location. So when you declare a variable, right, it's tied to an address, and that's how it's able to store data. Then for the next one, we're going to fill the Y. So Y is set at 3401. And so when you come across problems that don't tell you the address location, pick it. But when you fill it, trying to keep it together. Like I've been saying that for the last couple of labs, so that way you can check it in your simulator instead of going back and forth in different location. That's harder, right? We want to use the subsequent location. Okay. So your Y, we are going to fill Y at 3401. That's going to allow us to declare the label Y. So Y, we're going to do a dot fill hex 3401. So now we need to initialize X as decimal 3. Okay. So if we say X is equal to 3, first, we need to load the label X, okay? And then we're going to introduce the decimal 3 to that register. So we need to first load the X to the register and then add the 3. So that's what I did in 2 lines. So for us, X is equal to 3. For assembly, we have to do it in 2 lines, right? We can do an LD or an LDI or 1X. So we would load label X to register 1. Then we would add the decimal 3 to register 1. So your register 1 holds 3, which is X. Okay. And we haven't gotten to multiplication yet, but we will. So I'm going to introduce a little bit of it here for you. Okay. So Y is equal to 2X. And we already know in the previous step that X is 3. So, you know, you can't just assume that it will be 6. So technically it is 6 here, but we have to make it 2X. Okay. So we already know that Y is fill at a location. So we need to load Y. So here I put down the pseudocode. I'm going to load Y label to a register. Okay. Then I'm going to copy the X register to the Y register. And then I'm going to add for the multiplication because this 2X is equal to X plus X, right? So if you do 4X, it's X plus X plus X plus X. So we simply can just load the Y label. So that's what I did. I did an LDI R2Y. Okay. And I need to copy to the X to the Y because Y is equal to 2X. So I need to bring the X there and then I'm going to do it again, right? I'm going to add it again. So here I'm going to copy the X to register 2, which is Y. Okay, so register 2, hold the decimal 3 or X, which is also equivalent to Y. At this point, Y is equal to X at that line. Okay, but we need to make it 2X, so we're going to add it again, right? We know that your X is at register 1, right? and your y is also an x. So on the next line, you can do two ways. You can add it by itself, because the last we left it, register 2 is also x, right? Which is 3. So if I take a 3 and I add a 3, I would get a 6. So I can add it by itself, or I can go back and add the register 1. So you can do it this way, or you can do an add R2, R2, R1. It's still the same. Okay. Anybody get that or have confusion with that? So I can have it this way, or, right, I'm gonna change this, or I can do add R2, R2, R1, which makes it, you know, R2 is equal to X plus X, or Y plus X, and Y is equal to X in the last copy here. Okay, so you can do it this way, which is what I recommend, or put a lowercase, so, or you can do an add R2, R2, R1. So you would still get the result as in that will be equal to a 6, because it's 3 times 2 is going to give you 6. So it takes 3 and it adds 3 again, which gives you 6. Now, in the case where we have to multiply a lot, so let's say if we have y is equal to 10x, right? It makes more sense to do a loop with that than just to add it 10 times. We don't want to just keep repeating that same line. So you can write a function and just have it add itself 10 times, right? As a loop. Any question on this? Okay, so after we got the value, we want to store it out and we want to display, right? It says to, I would store it to a register, and then I can also do a, bring it to a register 0. So if you really want to display like what it says here, right, you would then need to copy it to register 0. So you have to do an add R2, I'm sorry, R0, R2, R2, which copy Y to R0. And then we can do a puts because it uses register 0. So doing it this way, you store it out to a location where you can use the simulator to check, but also if you really want to display in console, you have to bring it to register 0 by a copy. Okay. This will show on console. And then we can think about the halt in between, right? So we can, at this point, we can do a halt and so on, you know. So this is a sequential program, right? We load the X, we load the Y, we double the X as Y, we store out, right, the Y after we double it, and we also output it on console. So it's just gonna flow top down. Any question? So tracking your register, right, as the program gets longer is important, and looking at the values, okay? Now for the project, you don't have to put comment for every line, okay? We only did this because for practice reasons, so it helps you see it, but I will expect comment for various sections, so that way, like stack or, you know, array, when you set up an array and so on. Okay, anything with 6A. All right, let's talk about 6B. So we have a different criteria for B. Now we have 3, right? 3. And when I taught this in the last couple of years, I only give them the pseudocode. So I'm gonna give you some of it, and then you're gonna have to finish some part, because by this point, you should know how to handle some of these values. And if you haven't been able to complete the lab and things and you're not caught up, I recommend that you go back, watch the video, complete the lab, and so that way you can understand this concept and also reach out to me for help. Okay, so we have X, Y, and Z label are set from 3100 respectively. So that's easy. Our data section on the bottom, we would fill with X fill at 3100, Y fill at 3101, and Z is filled at 3102. Now the equation writes X minus Y plus Z is 10. This is a decimal value. Okay, so since we have the label location, we are gonna load them. We would have the X load to register 1, Y load to register 2, and Z load to register 3. I normally use sequential register so I can track them easily. It's really your choice, right? Just keep in mind that R0 sometimes needs to free up. So if you have some R0 there, you might have to clear it and copy things over. Clear it before you copy things over. So we want to load the label to the registers. And we can use 1, 2, 3. Then I'm going to handle, right, 2 things at a time. Okay. You can take X and subtract Y going left to right, or you can do this. Okay, so what I chose to do is I wanted to handle the positive things first. So I'm going to take X and I'm going to plus it with the Z, and I'm going to put that on R4. So since my X is in register 1 and Z is in register 3, I just load those. Then I'm going to put it into R4. Then now I'm going to handle the negative Y. So I can subtract Y. So that will be the next step. So here we would break it into, right, multiple subtasks. So now we are going to take the Y, which is in register 2. We're going to do the 2's complement so we can set up the negative Y. So right after that, I have to combine everything together to have X plus Y minus Z. So I know that X plus Z is in register 4. So now I just have to add the negative Y to that. So I would do an add R4, R1, R2. So by this time, my register 4 is going to be X plus Z minus Y. Now, I can't forget this, okay? So let me ask you this. How do you handle 10? What do you do next? Okay, so I gave you like 80% of that problem already. So how do you handle 10? How would we be able to take this value, right, and make it this equation? Anybody have any idea?
I think we need to free up another register, right?
So let's say I have register 5. Okay, let's do that. I'm going to do as you tell me, okay? So we can do an add R5, let's say that's our register, right? R5 and a decimal 10. Oops, I forgot the comma. So now our R5 is have a decimal 10. So what do we do next? We have to make sure that this and this is combined somehow, right?
Then we would add R5 and R4 together.
Okay, and then put it on, let's say R5. I'll do as you say. So add R4, let's say put it on R5 now. R5 and R4. So your R5 is gonna be X, right? Plus Z minus Y plus 10.
Well, that doesn't look right.
So what do you think? Algebraically, how can we handle 10? Because it's asking this right here is equal to 10. Is 10. How do you handle that? So if we do it this way, wouldn't it be like the same as doing this, right? So if I need to handle R10, if I was to do what you said, right, can I just do add it to R4? But that would just be equivalent to, right, your R4 is equal to X plus Z minus Y plus 10. Does that sound correct? So if we're here, let's say if we're here and we need to handle that, the last part, which is it needs to be equal to 10, right? This subtract this plus Z is 10. Can I do something with this? So Emmanuel, you can still go with what you had, but you need to make sure that it represents this part.
Yeah. I think we still need another register for 10, right?
So okay, so let's not do this. You're saying going back to put register 5. Okay, so we can do add R5 with the decimal 10. So my R5 is 10. And then what?
I don't know. That's where I feel like I'm getting stuck.
Anybody else? I'm sure some of you know this.
Do the 2's complement of 10?
Of R5? Okay. Yeah, so thank you. So here is I'm gonna put handle, right? We need to handle 10, okay? Decimal 10. So we can subtract it, right? Because algebraically, right, we have to move things to one side. So, and when you subtract it, you can branch it for 0. So if we rewrite this equation, isn't it really X, right, minus Y plus Z, right, subtract 10 is equal to 0, right? So here we have a 10, right? Or what you can do is, if you're lazy like me, you do this. You can do the 2 complement, or you can just introduce the negative decimal this way, right? So let's do the 2's complement as you recommended. So we can do a not R5, oops, R5, and then we would do an add R5 and a hex 1. So now our R5 is negative 10. And then we combine them, right? Add R5, sorry, let me scroll down so it doesn't block you. R4, R5, R4. which gives you everything subtract 10, right? X plus Z minus Y subtract 10. Okay, so how do we check for 0? Okay, then we can, so how now, right? When we took care of this part, okay, now we can branch to check for 0. So if everything subtract and if it's equal to 0, then we can do something else. Okay. Another way that you can also look at this is to move everything over and use a single variable and then store that out. Okay, so you can have Z is equal to, you know, Y minus X plus 10 and then store it out for Z. Okay. So as you can see, just having this equation, right, we have to really think about little pieces on how we would be able to handle them. And if you use it in an algebraic way, you have to think about how I'm going to end up with one label where I can store out the value. Because ultimately, when you solve this in math, you have to think about like how that would represent a certain value, right? If you have 3 variables, I wanted to know what Z is, I want to know what Y is, and I want to know what X is under a certain condition. Okay, so for this, when we get here, right, we have, so this is in your register 5, and we have to make sure that we think about how we would, I'm going to put a note for you, right, check for 0. Now, if you build out this part of the program and you test it and it's not to what you expect, you have to debug it. So I would debug this section, how I handle the 10. Okay, and that kind of go back to what we were talking about. Okay. Question. So this will be continuing. So we need to solve for Z if X is greater than 10 and Y is less than 5. Okay. So recall that your Z is in register 3. Okay. And this, we're using this equation, right? So register 5 has everything. So I put here that you need to check the condition for X is above 10. So we need to take that and subtract 10. We would branch positive because positive is gonna, when we subtract that, right, it needs to be greater than 10. So if I take 11, subtract 10, I have a positive number. If I take 10, subtract 10, I get a 0. So I, 11 is where we start. So that will be positive. So I need to branch positive and then go to positive. So here is where I check for X. And if X at register 1 subtract 10 is gonna be positive, it's gonna go to POS. And at POS, I'm gonna store it out to Z because it tells me here that I need to solve for Z, right? And so if we want to really store that out for Z in the prior section, you need to do a copy. So why is that? Because your equation is in register 5 here, and you need to bring everything over to register 3 to store it to Z. Can you store directly from register 5? Sure, right? I can eliminate this line and simplify it if I just store it like this. Oops. Okay. So I'm going to finish this part. I'm going to tell you what I would fix the second round, right? So when we do, then it needs to check the Y condition. So we need to check the Y condition that's below 5, right? I still have to subtract. So I'm going to subtract 5, but I'm going to use a smaller number like 4 minus 5. Okay, it's going to give me a negative. So I'm going to branch for negative going into neg. And then, and then I can store that out. Okay, for Z. So same thing. Or we can do something else with that neg. Okay. Now, with that said, if you look at the thing that this program really wants is it wants you to solve for Z, right? So coming back at the beginning of the program, you can simply solve for Z algebraically and approach it that way. So I can move everything over. So it can be that your Z is equal to X minus Y, 10 minus X, because you got to move everything over to the right, plus Y. And if we start out that way, right, that will be really easy because you're going to end up with one variable so that way you can store it out. Okay. And then let me change this since I changed my register. So at the end, once you have the store out to Z, if I want to display this on console, like what it says, display Z, right? Display Z can be in the simulator or on the console. So let's say if I need to do that, then I need to do a copy to register 0, right? R0, R5, hex 0. I keep forgetting the, yeah. And then I would do a load. Yeah, I would do a load. And then I would do a put. I'm sorry, no load there. And then if you want to display some text, then you would do an LEA, right? And a string. I think that's what I was thinking. So when we go through this, you can see that we go through the decomposition process, right? And it's really important to look at the piece of the problem statement on what it's really asking. Like solve for Z, that's what it's really asking. And in the case where, in math, we would say, okay, I would plug in a number that's greater than 10, and I would plug in a number that's less than 5. But in assembly, we would say, okay, solve for Z. So we want to make sure that we use the equation with Z as the variable that's going to store the result. And then we would apply the condition for these guys. So it's easier to check, right? When we handle the 10. Okay. So in the case that if we don't pay attention to that, you notice that we have to go back and, fidget some of the other stuff that's there. And then you're like, oh, well, I gotta make sure that I subtract this and move it here and get it over there and so on. And so that can change the whole structure of your program. All right. So the point that I want to drive from this is to make sure that we see how we would plan out our program, looking at the problem statement, write out the algorithm. This is what I'm going to use. This is the register I'm going to use. This is how it's going to branch. And at the end, I wanted to get the Z and show the Z. All right. Any question on the And remember that these are just snippets, right? To make it complete, you got to add all the other stuff and then .n at the end. Okay, so for C, we are going to use we're going to use A, B, C, and R. Okay, so we would fill the hex location for A at 33330. Now, also think about, like, we talked about memory location in the last few weeks. So when you're using immediate values, you got to be careful about like how your address range would be. Okay, and then we'll touch on the array later on. So sometimes you can't just go really far down because it will be outside of the address scope. Remember, it has like limitation with 255, the positive and 255 negative for the range. Okay, so here what we need to do is we need to fill A, B, and C. Let's remove this for now. Okay, and we say that if A minus B is greater than 0, we're going to put 3 onto the R. We've done this in the lab. Okay, so we would then fill the R at the subsequent. And then we would do a load. LDI R and A. I like to load everything at the beginning, but some people, they do it as they go with the label. That's up to you. Just like what we've done in the previous exercise. Then we would use the subtraction, right? So we would then set up the 2's complement for B and then do the A plus the negative B. So not R2, R2, and then add R2, R2 with the hex 1. And then we would do an add. We can use another register, R4, R1, and I'll just use R2 and R1. So here is where we have R4 is equal to A minus B.
Professor,
Mm-hmm.
does it matter? I know you changed R2 and R1. What if I put an add R4, R1, R2?
The
Does it make a
same.
difference?
It's the
Same.
same. It's like saying negative B plus A. Right? It's like saying this, negative B plus A. Isn't that the same as A subtract B?
It is, but you changed it. I thought it made it.
Yeah, you can do that too. You can do this. Yeah, if you wanted to flow that the way that it should be, right, from left to right, but the value is still going to be the same. So now I have this. Yeah.
Okay.
Mm-hmm. Yeah, it's still going to be the same value, whichever order, because it's addition, so it can't modify the sign. Okay, so now we can branch, right? That's easy. We need to check it that it's greater than 0, so that's a positive. So we're going to do a BRP, right? Actually, yeah, BRP. And I can say greater or something like that. And because then, you know, subsequently, because it's branched to greater, right? then we can send it to the grader, which is gonna be, we'll just put it on the same line. We need to add, so here I will have to load register. Let's do register 5 with the R, and LC3 simulator doesn't like using R too much. Sometimes, you know, it might throw an error, so you can do like RES or result or something like that, right? But we'll just use R right now. And then we would do an add R5 with a hex 3 or a decimal 3, same. Five is a 3. Because it tells you that here, so that's why we need to fill that there, right? Register or to fill to that, so we can check. Oh, did the 3 pop up at that location when we simulate it, right? Everybody okay with that? Assembly can be pretty fun. After a while, you're like, oh, that's easy. So just for this, okay, we broke it into pieces, right? We load each of the variable, we add them together with the two's complement, then we check for a positive, and then we send it to a label. And in that label, we add the 3 to R. Any question? We've done this in the lab a few times, so. Now, you can do these next ones. I think I did this with my other class last year. All right, I have time, so I'll walk you through it. Okay, so this section is easy, right? We already have everything set up here. So if you want, you can recopy this down for the next one, but I'm just going to continue with this program, right? Recalling that these are the registers. So the only thing that we're going to change is the branch and the label. I don't want the bullets. Okay. So the only thing that we're going to change is this part. Less. And we're going to change to branch to end, and we're going to make it less. And for the less, section, it tells us that we're going to subtract 2 from R. So here we would then need to load R again, and then we would need to, you can do it this way, negative decimal 2, right? That will be negative 2. Or you can do the 2's complement, which we should do. Not R5, R5, add R5, R5 with the hex 1. And so therefore R5 is, oh, sorry. Let's do it. 5, okay. It's 2 here. So when you do that, your R5 is a 2, right? Which is R is a 2. And then when you not it, it will subtract 2. You can use another register for that. Like if you want to do like R6, like this, you can also just do a not R6. Okay. I just reuse the register, so. Or at that point, it will be R minus 2. Load register, load R to register 5. Add 2 to it, so that will be R. I think I have a misstep here. Sorry. So R5 is 2. I don't like this. Sorry. I want to do this so it's clear. Yeah, otherwise I think I should use another register and do the subtraction so it's a little clearer, because when it comes up like that, sometimes, you know, you can have wrong data. Okay. So we are going to branch it now for equal to 0, which is really easy. Okay. And then don't worry about testing the program, just finish this part. So we're going to do a BRZ, right? Go to 0. Okay. For the next bullet. And then we want to take R and we're going to 0 after the subtraction, we're going to add the 1. So we can simply do an LDI R5 to R, and we're going to add R5 with a decimal 1 or a hex 1. And so what you want is all of these branches needs to be together, okay? And then you can have the label section following. So in a regular program, you would have BRN less, right? BRN greater, or BRP greater, BRN less, BRZ 0. And then after that, you can have your label greater, less, 0. Okay, do not separate them like this. It's not going to be able to check, you know, your register from the prior line. I hope that you understand what I just said.
After each branch, will we put a halt as well?
Yeah, in the label section. You know what I mean? Yeah, in the
Yeah,
label,
okay.
in the greater, less, and 0. So in a regular program, you would do like, I'm gonna come back on top here, right? Like how we would have it. This is like a normal program. We would do a BRN, right? And then we would have less, and then we would do a BRZ, right? And then we would have 0. And then after that, you would have the subsequent label section, right? Greater, and then you can say halt, and then you would go less, right? And then your less section, and then your 0 section, and so on. Okay, so together, when we piece it together, it should have like the branches. So if this doesn't check true, it's going to go here. And where is it going to check? The last register, which is register 4. Okay. And if this doesn't check true, it's going to go here and it's going to check register 4 again. Right. And so if this checks true, it's going to go to that 0 section. It's going to do its thing. And then it's going to flow again sequentially after that. So when we map this, right, we map it to greater than 0, less than 0, and is 0. And so, and you don't need to fill those branch label sections. We only gonna fill the variable section. Okay. And then if you're fancy, you can store out to store out to R, you know, but it doesn't say that in the problem statement. So we're good there. We'll just check it with the set value. Okay. And I hope that helps. So if you wanted to see everything together, you can put it together like this. I think I did. Oh, yeah. Hey. Oh, I was trying to show them how to do like multiplication with different x's and so on. Okay, any question? That's all she wrote for today, really. So I'm going to stop recording.